All right. Well, at this point, it's just Eli and Sadie. So, what? I'm talking about students, Robin. Sorry, my kid's being annoying. So Eli and Sadie. So yeah, you guys have any questions or anything you'd like to go over?
Could you go over like a Newman projection one?
Ooh, a Newman projection.
Just like refresh us on it.
Yeah, let me see how close to the board I can get you and still have room. Let's see. Okay, so Newman projection is when you basically draw along a particularly indicated bond in a compound. All right, so let's say, we had something like that. All right, and you were tasked with drawing the Newman projection. So basically what you do, or the way we did it, was we would take these two carbons, we would assign them a dash, not a dash, excuse me, a dot and a circle, right? So one of them's the front carbon, that's the dot, and one of them's the back carbon, that's the circle. It can be either way, right? But what we did was we just went ahead and assigned one of them. Like in this one, for example, I could assign this one to be the front carbon and this one over here to be the back carbon, right? There's going to be bonds. There's going to be 3 bonds coming from each one of the carbons. All right, and then you assign the groups. All right, so in the back, if you look at this carbon, you look to see what else does it have on it. It's got an ethyl group, it's got a methyl group, and not drawn, it's got an H, right? So you want to put those on your Newman projection. They can be basically in any order starting off. Then you do the same thing with the front carbon. You look at this carbon, it's got 1 methyl group and then 2 H's. Okay, so again, the first assignment's kind of arbitrary, so we're going to do it like that. All right, that is one of the Newman projection formulas. All right, so kind of thinking about context of like a multiple choice test or something, I honestly don't remember how they ask or what they ask about these, and that's probably a good thing. I don't want to lead you in the right direction subconsciously. They could, give you like 4 different Newman projections. They could ask you which of these is a legitimate Newman projection for this compound. They could ask you about stability, right? Which one of these is the most stable one, right? Do y'all remember talking about staggered and anti?
Yeah, a little bit.
Yeah, staggered, basically for staggered and anti, you're looking to see these bonds, the bonds on the front carbon and the back carbon, are they like overlapping each other, or are they sort of, kind of staggered from each other, sort of offset, right? So this one is a stagger. We can also describe the relative positions of the biggest groups. Like, for example, on the front carbon, out of these 3, CH3 and the 2 H's, the biggest group is CH3. On the back carbon, the biggest group is the ethyl group, right? So you can also describe how the biggest groups on each carbon are oriented with respect to each other, right? When they're completely opposite from each other like this, that's called anti. So this is a staggered anti. Okay. So if we wanted to go through and we wanted to draw the rest of them, all we have to do is basically just pick one of these, either the front carbon or the back carbon. Doesn't matter which one, as long as you keep it consistent the whole way. I always like to rotate the front carbon personally, and you rotate it 60 degrees every time, right? So if you did this again, you wanted to draw the second Newman projection. We're going to leave the back the same. We're going to rotate the bonds in the front, right? So if we rotate them 60 degrees, that means they get rotated sort of directly in front of those other bonds, right? I'm offsetting them just a little bit when drawing, but realistically, if we had like a model or something, they would be directly kind of overlapping each other, right? Or eclipsing each other. This is called an eclipsed conformation. All right. So what I did was I chose to rotate this. Again, you can go clockwise or counterclockwise, doesn't matter. Just do it the same direction every time. I'm going to say I rotated this clockwise. So now I have this methyl group over here, this H over here, and this H over here. All right. Do you remember, so what do y'all remember about stability? What's more stable, a staggered or an eclipsed?
Staggered.
Staggered. Staggered's always going to be more stable than an eclipsed, right? No matter what. We could rotate it again. Rotate it another 60 degrees, and that means you're going to rotate into another staggered conformation. But now this CH3 is going to be down here. This H is going to be up here, and this H is going to be over here. All right. So this is also staggered. However, it's a little bit different from this one, from the first one, because the two biggest groups on the carbons, they're not completely opposite anymore, right? They're actually sort of kind of next to each other. We said that this has a term called gauche or gauche. Okay. Staggered anti is more stable than staggered gauche. All right, so not all staggereds are the same. Not all eclipses are the same either, right? For some reason, they don't give any special terms to those though. So whatever. But for example, if we did this one more time and we rotated like this methyl group in front of that ethyl group, that would be an eclipse. And that would be a really, really unstable one. That would be even more unstable than this one because you would have the two biggest groups in front of each other. So, and you keep going until you rotate it all the way around. So, you know, you should probably end up, if you're drawing these from scratch, you'd have like 6 Newman projections. Okay, Robin, thanks. Don't let Shadow out. Does that ring a bell?
That sounds good.
Okay, cool.
Is there anything else you think is particularly important to know? Like basically everything, I guess.
More or less. I mean, it's a review, or it's a test based off of both semesters. Now that being said, I mean, you've used a great deal of your OChem I knowledge this semester because you had to have it to do stuff. So there's nothing in particular I think you need to like study. I would say, you know, study what you think that you need brushing up on, what you're weakest at. Here's one piece of advice. One thing I see sometimes is that people will kind of give away some of the easiest questions on here. They'll miss the easy ones. Probably because it's been a while since we've covered it in OChem I. So maybe go back and brush up a little bit on some of that stuff. like the chapter 1 stuff, doing Lewis structures and resonance structures and hybridization, boiling point, melting point from chapter 3, right? Those are the easy questions, so you don't want to miss those. Yeah, that's probably one good piece of advice as far as specifics, but really just whatever you think you're kind of weakest at and you need most work on. They spread out the questions pretty good. There's a wide variety, so they don't just dump like a whole bunch of one type in there. Oh, hold on one second. Where?
I'll show you. Shadow.
Stay.
Buddy.
Okay.
So cute. Oh my goodness. What did you say his name was? Shadow.
Okay, sorry, I'm back. We actually have a student in person.
Are you using chemistry?
All right. Okay, Robin, don't put them on the table. Remember, Kirsten's here for a review, so we don't want to monopolize her time only with Shadow. My dog's here, by the way. So he's, yeah, Kirsten said you're missing out. My wiener dog is walking across the table right now. All right. Yeah, so that's kind of it as far as specific subject matter. One thing that you haven't seen before on an exam is the stuff we just did in chapter 22, because we just did it and it hasn't been on one of the other exams. So be sure to get a good bit of practice with that. Be sure to work that sapling, even though it's ungraded. I think that will help out a good bit. So, all right. All right, Kirsten, Sadie, Eli, what else would you like to know?
Like anything heavy from organic one that we need to...
Is there going to be anything heavy from organic one? Well, we're kind of talking about that a minute ago. The people who made the exam did a good job of really kind of spreading out subject matter from the whole year. So there's not one particular area that's emphasized over others, I don't think, from memory. One bit of caution I was telling Eli and Sadie is that try to make sure not to miss the easy questions, because I do see that sometimes. People will miss some of the easy stuff at the beginning because it's stuff we did an early in organic one. So, something like recognizing the hybridization of an atom, right? Whether it's SP or SP2 or something like that. Drawing a resonance structure. Answering a question about the acidity effects, right? Picking out something that has the highest boiling point or whatever, right? those are, I don't want to say gimme questions, but they're definitely easier than a lot of the reaction heavy questions that come later on. So yeah, like for example, if you can like zip through the first 10 questions and like get those all right, that puts you at a big advantage for the rest of the exam.
Are you saying like this test gets harder as you go?
Not necessarily harder, but it progresses to more complex material, right? It doesn't necessarily follow the format of our book, exactly, but in general, it kind of progresses sort of like we did through the topics, the whole year. Yeah. So there's much more organic 1 stuff in the first part of the test, more organic 2 stuff later in the test. Like spectroscopy is not till like closer to the end.
Right. What are some of like the OChem reactions?
Reactions of alcohols for sure. Reactions of alkyl halides. So those were the SN1, SN2, E1, E2 reactions. So that'll be on there for sure. Other reactions that we did in OChem I, we talked about reactions of ethers and epoxides. Those certainly could be on there. They're not going to be probably represented as much as alcohols, I would imagine, because alcohols are more versatile. But you might see something with those. Depending on what you define as organic 1, like when you took organic 1, we did alkenes the first semester.
Right.
This time we did it second semester, so that's kind of on the borderline. But you'll definitely see some alkene reactions on there. We didn't do as many in organic 1 because we had to do all the preliminary stuff, but there's definitely some out there.
How long do we get again to take it?
2 hours. And again,
Questions for them?
70 multiple choice. And again, you probably heard me ranting about this yesterday, but I want to reemphasize it. Make sure to take advantage of the 2 hours. I mean, I see so often, you guys have had did you guys take, or you haven't taken the Gen Chem standardized final, have you?
I think we took one with Andy Thomas.
Okay.
Maybe the first semester, an older one. I don't know what it was exactly.
You have. Yeah. These ACS chemistry exams, they, if you've had one before, they're a bit of a grind. They'll wear on you. So a lot of people will just kind of answer what they can answer immediately, and then they'll kind of give up because they just want to get done with it. So also people like turning in their exam in half an hour or something, and I know that's not enough time for you to sit there and thought through stuff. Being blunt, you're going to miss some questions on this exam. It's a standardized test, so you want to make sure to grab as many as you can, because one of the things I have like a formula that I use for the curve, and a lot of that's based off of the national percentile ranking you come in at. Right, so make sure to take advantage of that time. Do what you can, and sit there and think and solve and strategize. Use that multiple choice strategy where you eliminate obvious answers and try to work it out to solve between 2 of them. Yeah. So sorry, my dog is acting crazy over here. So. In case you would like to see. Oh, there he is. He's Shadow. He's a dachshund.
That's the 3rd animal that's been in there this week.
Yeah, I know Annie brought her cat.
Matt brought his dog, too, to one of the meetings.
Oh, really?
His little he was a boxer. It was running up and down the steps all the way around.
Nice. Yeah, sometimes Bunker will bring his dog, Carl. Helms at times has brought his dog. He's got 2 dogs now, but one of his dogs. So yeah, it's fun. Yeah, it's fun for the dogs, fun for the students. I've thought about bringing Shadow for your final exam, but I'm afraid he'd be too much of a. I think he would be too much of a distraction. He's not one to just lay there and kind of. I was hoping he would be, but this was kind of a test run. But I think he's a little bit too energetic. Yeah. So maybe when he's older.
I think I'm good, so I'm gonna go do some studying. Thank you.
All right. Cool. Sadie, do you have any questions?
I just had a question about like when I was going to take it.
Oh yeah.
Like how that's gonna work.
Right, because you're in quarantine.
Yeah.
Okay, so what we will need to do then is we will need to obviously set up a Zoom. And so what I'll do is I have like a test booklet. I'll just kind of scan all the pages and put them into a PDF. When would you be available to take it? Like, you want to do it at the regular exam time?
I can, or I can do it after they're done so that I'm not
That's fine too.
distracting them or something. I don't know.
Yeah, on Friday I'm more or less open. So like Friday after they finish, let's just say like 10 o'clock or so, then I can do it basically anytime between then and 2:15.
Okay, we can just do like 10 o'clock on Friday because I don't have anything else.
Let's make it 10:30.
10:30.
Just to give me time to get set up and acclimated and everything.
Okay.
Okay, yeah, I can do that.
Okay, sounds good.
How are you feeling?
I'm good. I don't have any symptoms, so.
How's your boyfriend? Is he?
He doesn't have any symptoms. We're just
that's
chilling
good.
out, basically.
That's good. So not. Yeah, good. I'm glad.
Yeah, kind of a rough time to be in quarantine, but.
It is, yeah, it's bad timing.
Yeah, it's a little bad timing, but it works. So.
Cool.
Yeah. Okay. Well, thank you.
Yep. Kristen?
Would you want to do a Newman projection?
Oh man, I just did one. I'll do another one, or I'll do it again. Okay. So if you're watching this video, I'm about to do the same exact problem that I did a minute ago. That's okay. All right. So Newman projections.
Dad wants to help.
I'm sure he does. All right. So let's see. Okay. So when you do a Newman projection, basically what you're doing is you're taking a structure and you're sort of drawing it like you're looking down the barrel of it like that head on. All right. So you have an indicated bond here. That means you're looking at the 2 carbons that are involved in this bond. All right. And so you can represent those with a circle and a dot. The circle is the back carbon. The dot is the front carbon. And like if you're doing this like from scratch, sort of like what you do on my test and stuff, you can assign either one of these to be the front or back. Doesn't matter which one. Right? Just for argument's sake, I'll call this one the front carbon and this one the back carbon. All right. Each carbon is going to have 3 bonds coming from it. So the back carbon bonds look like that. Front carbon bonds look something like that. Okay. All right. And then you start assigning the groups that are on these carbons. Like the front carbon, right here. It's got a methyl group, and it's got 2 H's that we didn't draw, but they're still there. Okay, so I can represent those on those bonds. This carbon has an ethyl group, a methyl group, and an H again. All right. Now, where I actually put these is pretty much arbitrary the first time. I can put them anywhere I want to the first time, and then everything else is based off of this. All right. So this would be one of the Newman projection formulas. Okay. All right, do you remember the term staggered and eclipsed?
I think so.
Okay, basically staggered and eclipsed refers to whether the front bonds are directly overlapping the back bonds or whether they're sort of offset like this. These are offset and they're called staggered. Okay, so that's one descriptor. Another descriptor that you can use specifically with staggered conformations is is anti or gauche. All right, when you're doing anti or gauche, that's basically a descriptor of the relative positions of the biggest group on your front carbon and the biggest group on your back carbon. Biggest group on the front carbon is methyl, biggest in the back is ethyl. They're completely opposite, so those are referred to as anti. All right. Staggered anti is always the most stable conformation. That's the lowest energy. All right, so draw a second one. Just keep our circle in the dot. You pick one of them, either the back or the front carbon, and keep those groups exactly where they are. I always like to keep the back carbon groups in the same spot. And then what you do is you rotate the other one 60 degrees. And this can be clockwise or counterclockwise. Just make sure you can do it the same direction every time. I'm going to rotate the front bond or the front carbon groups clockwise 60 degrees. And when you do that, you go from a staggered to an eclipsed conformation. And since I'm doing this clockwise, that means the methyl group is now shadow, flash. It rotates in front of that H. Right? This H rotates in front of the ethyl group, and this H rotates in front of the other H. All right, so this is an eclipse conformation. All right, we don't have a second descriptor term like anti or gauche for these, but do be aware that not all eclipses are the same. Right, like in this case, we have the ethyl group and an H eclipsing, methyl group and an H eclipsing, right? Later on, we keep turning this around, you could end up with an eclipse where the ethyl and the methyl are eclipsing each other.
And that's less stable.
That's less stable because of steric hindrance. Yep. And we do it another 60 degrees. We see another staggered conformation. But it's not the same staggered conformation as before, right? Because now the two respective bigger groups, they're not anti to each other. They're closer together, right? This is the gauche conformation. All right, staggered anti is always more stable than staggered gauche. But staggered gauche is more stable than any eclipse.
Okay.
Yeah. Shadow. No, this is why you can't be in there on Friday night. All right, so you can keep going with this. So, you make the full 360 degree circle, and you basically go through 6 Newman projections. Sometimes you run into duplicates, sometimes you don't. Does that help?
I guess what would the multiple choice question be asked?
Good question. What would a multiple choice version of this look like? They could give you a structure, sort of like that structure with the arrow up there, and they could give you 4 Newman projections, and they could say which of these would not be a legitimate Newman projection formula for this, or which of them would be a legitimate Newman projection. They could give you 4 Newman projections. They could ask you which one is most stable, right? They could give you some Newman projections and ask you to say which one of these represents an eclipse, right? Stuff like that. Shadow. So is that your major concern, is the organic one stuff? Kind of, I can believe that because, yeah, you didn't.
But I'm not.
Yeah, you not only were you not in here last semester, it's been like a few years since you've had it. Yeah, we've been using a lot of stuff though from OChem 1, throughout. We learned about resonance in OChem 1. We've been doing resonance. We learned about hybridization, recognizing whether something's like SP2 or SP3 or whatever. We've been using that. We even revisit the acidity effects sometimes. So yeah, but there are some unique things that pop up. Newman projections would be unique. There might be a couple of questions about chair conformations.
That would be a good one to go over.
Okay, yeah, we can do that. There'll probably be something I would guess about physical properties like melting point, boiling point, solubility, that kind of thing. Sure. You know where his leash is? Oh, sorry.
And there,
Yeah, there's poop bags.
I guess.
Yes, I did. Okay, so we did chair conformations basically with substituted cyclohexanes, right? So like, for example, let's say we had cyclohexane and then, I don't know, let's just say we had like CO or something like that, all right? Okay, so if I just draw that, and one thing that could be asked, like on a typical exam of mine, would be, okay, draw all possible chair conformations. So I'll show you how to do that, and then we'll talk about how multiple choice might come into play, right? So to draw chair conformations, first of all, you got to figure out how many you're going to need. Remember that if you have two components on the ring, there's two possibilities. These could be cis to each other, which means they would be on the same side, like both on dashes or both on wedges. But you could also have trans. So if I draw them like that without any dashes or wedges, that means you have to draw all of them. If I drew specifically the cis arrangement, you'd only have to draw the cis ones, right? For both cis and trans, there's going to be two chairs. All right, so for this one, we would need to draw 4. All right, so when drawing, first thing you need to do is know how to draw the chair. Remember, it's got that little lightning bolt look to it. And if you use your imagination, beach chair. Okay, so look to see on your structure where the components are. Like in this one, if we define this one as carbon number 1, we would have another substituent at number 4, right? So pick out a carbon. Again, it's arbitrary. You can pick any one. I always like to pick out the ones on the end whenever possible, right? So I want to work with those. You remember axial and equatorial bonds, the names, sort of?
I know one straight up and
Yeah.
down.
Yep, so you always have one axial bond on a carbon, and you always have one equatorial. The axial points straight up or straight down, right? The equatorial one's always at a slant. Okay, and this is probably the thing people forget the most. Always remember this when you're drawing. The axial bond goes in the same direction as the carbon it's on. So like this carbon is pointed up, right? It's sort of on an upward point, right? So the axial bond goes straight up. The equatorial bond always slants opposite. All right? So I'm going to say this is number 1, 1, 2, 3, 4. I'll draw an axial bond there and an equatorial bond there. All right. So I've got my bonds. I'm not going to worry about the bonds on the other carbons because they're just all H's. They don't matter. All right. Now I want to draw my components. Let's say I'm starting off with a cis. We want to draw specifically a cis arrangement. All right. Well, what I'm going to do is I'm going to pick one of the carbons. I'll just pick this one. And again, I can arbitrarily put that Cl wherever I want to. I'm just going to put it over here. And that means the other guy is going to have an H. All right. So now I've got to put a Cl and an H on these 2 bonds. Right? Now, I can't be arbitrary here. I've got to put it in one of the specific spots. Where do you think the Cl is going to go?
Axial.
That's what most people say. It's actually equatorial. Cis and trans, whenever something's cis, that does not mean both axial or both equatorial. It means they're both in the same direction, up or down. So since this one's pointed up, we also want this one to point up. Now it's only on a slant, but it's still up.
Right.
Does that make sense? Yeah, and so that is one of the chair conformations. All right, to get the second one, you have to do something called a ring flip. That's where literally you kind of pretend that you're taking this beach chair and you're slanting this end down like that, and you're taking this side and moving it up. All right, so drawing the flipped ring is kind of tricky sometimes. I'm a lot better at drawing the forward chair than the reverse chair. That one's not too bad. Okay. All right. Now, whenever you draw the reverse chair, always remember, whatever was axial becomes equatorial. Whatever was equatorial becomes axial. So this equatorial down H now becomes an axial down H. Axial up Cl, equatorial up Cl. And then do the same thing with these. And those are in equilibrium with each other. Okay, does that make sense?
Yep.
Okay, then you would go through, start over, and do the same thing for trans, right? Shadow. So the easiest thing to do here is just leave one of them the same and flip the other one. And you can see the CLs here are trans to each other because they're pointed in opposite directions, even though they're both X. All right, you can do a ring flip. And just like last time, whatever was axial becomes equatorial, and vice versa. Okay. Any questions on how we drew them?
No.
Okay. Now, interpreting stuff about it, right? Again, just like with Newman projections, probably one of the most obvious questions that could be asked would be stability. All right. Here's a question. Look at the cis ones, just the 2 cis ones. Sometimes the equilibrium, or excuse me, sometimes within a system, one of the chairs is more stable than the other. Sometimes they're equal, all right? What do you think about the two cis ones? Do you think they're equal? Do you think one favors over the other? What determines that? You may not remember, it's been a while.
I don't remember.
Here's what contributes to stability. You want larger groups on equatorial bonds.
Okay.
Because that means literally they're further away and there's less steric hindrance, right?
I almost said
Yeah, when in doubt, stay steric. So like over here, right? In this structure, out of the two atoms, Cl is obviously bigger than H, right? So in this structure, we have one Cl axial, that's bad, I guess you could say for stability, one equatorial, which is good. In the ring flip structure, one axial, one equatorial. So they're equal to each other.
Yeah.
And that's actually why I drew the equilibrium arrow like this, because equilibrium does not favor one side or the other. All right. Look at the trans. Can you tell me if there is a difference in stability with the trans structures? Which one's more stable?
the one on the right.
One on the right. Yeah, definitely. Both components are equatorial. And in fact, you know, they could ask, okay, out of all possible chair conformations, what's the most stable one? So out of these four, it's that one. All right. So when we did this in OChem I, we did it for two contexts. We did it for dye substituted like this. This is the more complex situation because you can have four. We also did it just for mono substituted. So like if you had like one component hanging off like a Cl or CH3, if you only have a mono substituted ring, then you're only going to have two possible chair combinations. Now in real life, of course, you can have like 3 components on the ring and have like a bunch more than this even, but you're not going to encounter that.
Okay.
Cool, good question. Oh, one other thing I forgot that we did first semester was IR spectroscopy. We did that in lab. Now, Shadow, sorry about that. Now I gave some, with the NMR problems, right? They also had IR with them. So I don't know if y'all, how much you use the IR. But that might be something to kind of look over again. Unfortunately, you don't have correlations tables with this one. So that being said, I can probably highlight some specific signals, some of the ones that are more common that you might want to kind of try to remember the ranges for. The CH stretches for sure, all the different types of CH stretches. The OH stretch, that's a big one. The C double bond O stretch, which is in a carbonyl. C single bond O. And the OOP bands for aromatic compounds. There's other important ones for sure, but those are going to be the ones probably that are most common. So if you're making a priority of what to look at, those are probably the biggest priority. And yeah, there's like 4 or 5 spectroscopy questions, and they kind of mix NMR, HNMR, IR, and then carbon-13 NMR, which I went over in like 5 minutes the other morning, but it's a super simple type of NMR. So.
What about EZ?
EZ, yes, that's stereochemistry of alkenes. All right. Shadow, shush. So if you have an alkene, all right, here's the simplest alkene you can have, right? Sort of back up a little bit. That's ethene. That's the simplest one you can have. All right. Now, we can describe an alkene as being substituted basically when you have R groups in place of these H's, right? So like something like this. That's mono-substituted, right? So we can have one, right? And then you can have two. You could have two groups on there, right? Right? This is one of the ways you could have two groups. You could have them like that. This is di-substituted. And that's geminal, or gem for short. We're not as interested in that one. But the next one you probably remember. You could have two R groups on opposite carbons. Like that, right? This is di-substituted. But trans, right? So cis-trans is not just for rings, it's also for alkenes, right? So it's because these R groups are on opposite carbons and on opposite sides of the double bond, that's trans. And we can have them on the same side of the double bond. That's cis. Hey, Shadow. We'll go home soon, don't worry. I said we'll go home soon, don't worry. Okay. Then you can have also tri-substituted, and you can have tetra-substituted. Okay. Cis and trans refer to specific types of di-substituted alkenes. E and Z refer to the stereochemistry of tri and tetra. Okay. And so you'll see a lot of times they're kind of used, I don't want to say interchangeably, but they're very analogous to cis-trans. All right, let me illustrate. So if we had that, all right, would you say that's a cis alkene or trans alkene?
Cis.
Cis, yeah. And if we drew this, further, we see that, okay, the biggest group on this one is a methyl group. The biggest group on this one is a methyl group. The two biggest groups are on the same side. That means it's cis. They don't have to be identical to each other. This could be an isopropyl group. Again, the two biggest groups are on the same side, so it's cis. Now, you could have a tri-substituted species. Something like that. All right, even though we have a tri-substituted, we can still use the same logic. Shadow, no. On this carbon, we have a methyl and an H, right? This one's higher priority. On this one, we have an isopropyl and a methyl. Which one of those two is higher priority? Isopropyl. Those two groups are on the same side. So that's analogous to cis, but we use a different terminology. We use Z for that. Now, if this was changed a little bit, and one of those methyl groups was pointed downward instead. Here, highest priority group, H or methyl, it's the methyl. Higher priority group, isopropyl. They're on opposite sides. That's analogous to trans, but since it's tri-substituted, we use E, right? So use that classification system with tri and tetra-substituted alkenes.
I think that's all I really can think of.
Okay. All right. Well, if you think of anything else, we got till what, Friday? It's just, send me an email, drop by my office, whatever. We're happy to work on it. All right, cool. All right. So, also apologies to you and whoever's watching this for my barking dog. Like I said, I really was kind of thinking of bringing him as kind of like one of those therapy dogs, help to relax and stuff, but I just don't think he's ready for that yet. So, but you can enjoy his cuteness, from that little snippet where I put the camera on him. So, all right, I want to shut this meeting down. Goodbye.